Welcome to today's session. In this problem walkthrough, we'll be exploring problem number 1462, Course Schedule 4. This problem challenges us to determine prerequisite relationships between courses, testing our skills in graph traversal and query evaluation. Let's dive in and take a closer look at the problem. In this problem, we are tasked with determining relationships between courses based on their prerequisites. You are given an integer n, which represents the total number of courses, labeled from 0 to n1. Additionally, you are provided with a 2D array called prerequisites, where each entry, A, B, indicates that course B must be completed before course A. Another input is a 2D array called queries, where each query, U, V, asks whether course B is a prerequisite for course U. Your goal is to return a Boolean array result that corresponds to these queries. For each query, if course V is indeed a prerequisite for course U, the result should be true, otherwise, it should be false. The problem specifies that the number of courses n can range from 1 to 100, and the size of the prerequisites array is bounded by the maximum number of potential directed edges in the course graph. Similarly, the queries array can contain up to 10,000 queries, so efficiency will be an important consideration when solving this problem. Let's look at a concrete example to better understand the problem. Suppose n is 2, meaning there are two courses labeled 0 and 1. The prerequisites array is given as 1, 0, which means course 0 must be completed before course 1. Now, for the queries array, we have 0, 1, 1, 0. For the first query, 0, 1, the question is whether course 1 is a prerequisite for course 0. Since there is no such prerequisite relationship, the result is false. In the second query, 1, 0, the question is whether course 0 is a prerequisite for course 1. Based on the given prerequisites, this is true. Therefore, the output for this example is false, true. Now, consider another example where n is still 2, but the prerequisites array is empty. This means there are no prerequisite relationships between the courses. The queries array is 1, 0, 0, 1. For the first query, 1, 0, since there are no prerequisites at all, course 0 is not a prerequisite for course 1, so the result is false. Similarly, for the query, 0, 1, course 1 is not a prerequisite for course 0, so the result is also false. Therefore, the output in this case is false, false. This example highlights that if no prerequisites are provided, all queries will result in false. Let's examine a third example where n is 3, and the prerequisites array is 1, 2, 1, 0, 2, 0. This means course 2 is a prerequisite for course 1, and course 0 is a prerequisite for both courses 1 and 2. The queries array is 1, 0, 1, 2, 2, 0. For the first query, 1, 0, course 0 is indeed a prerequisite for course 1, so the result is true. For the query 1, 2, course 2 is a prerequisite for course 1, so the result is also true. Finally, for the query 2, 0, course 0 is a prerequisite for course 2, so the result is again true. This example demonstrates how prerequisites can involve indirect relationships, which must be considered when solving the problem. There are a few key edge cases to keep in mind when approaching this problem. First, if the prerequisites array is empty, then all queries will return false, as there are no prerequisite relationships. Second, when there are many indirect prerequisite relationships, it is important to account for transitive dependencies. For example, if course A is a prerequisite for course B, and course B is a prerequisite for course C, then course A indirectly becomes a prerequisite for course C. Additionally, for large input sizes, especially when the queries array contains up to 10,000 queries, the solution must be optimized to avoid exceeding time limits. Finally, you should also handle cases where courses are isolated or disconnected in the graph, as they will not have any prerequisite relationships. These considerations will help ensure your solution is both correct and efficient. In this problem, we are tasked with determining if one course is a prerequisite for another, based on a given list of prerequisites and multiple queries. To approach this, let's first consider the brute force solution. Here, we construct a directed graph where an edge from course B to course A signifies that B is a prerequisite for A. For each query, we perform a graph traversal like DFS or BFS starting from the source course to check if the target course is reachable. While this approach is straightforward, its main drawback lies in inefficiency. Specifically, for every query, we repeat the traversal, which becomes costly when the number of queries, q, is large. The time complexity is O, q asterisk, n plus e, where n is the number of courses and e is the number of edges, and the space complexity is O, n plus e. Next, we have the Floyd-Warshall algorithm. This method pre-computes the transitive closure of the graph, giving us a Boolean matrix that indicates whether there is a path between every pair of nodes. Once this pre-processing is done, queries can be answered in constant time, O1, by looking up the matrix. However, the pre-processing has a cubic time complexity, O, n cubed, which can be prohibitive for large graphs. Lastly, we have the optimized BFS or DFS approach with pre-processing. Here, we pre-process the graph to compute reachability for all pairs of nodes. By storing this information in a reachable map, we can answer each query in constant time. This solution pre-processes the graph in O, n plus e, time and balances efficiency better for sparse graphs. However, it does require O, n squared, space, which can become significant for dense graphs. This trade-off in space versus pre-processing time is a key consideration. For this problem, we choose the optimized BFS or DFS approach with pre-processing as our strategy. The key insight here is that pre-processing the graph to compute all pairs reachability allows us to reuse this information for multiple queries, avoiding redundant computations. This makes the solution especially efficient when the number of queries, q, is large. By leveraging graph traversal methods like BFS or DFS, we pre-process the graph in O, n plus e, time, which is significantly faster than the O, n cubed, required by Floyd-Warshall, particularly for large graphs. Once pre-processing is complete, each query can be resolved in constant time, O1, by simply checking if the target course is in the reachable set of the source course. This strategy works exceptionally well for sparse and moderately dense graphs, which are common in course prerequisite problems. However, there are trade-offs to consider. The space requirement for storing all reachable sets is O, n squared, which could become problematic for very dense graphs. Additionally, implementing this approach is slightly more complex compared to Floyd-Warshall. Despite these trade-offs, the pre-processing approach strikes the right balance between pre-processing time, query efficiency, and space usage, making it an ideal choice for this problem in most practical scenarios. To understand this problem, imagine we have a directed graph where each edge represents a prerequisite relationship, such as course dependencies or task sequences. Our goal is to determine if there's a path between two nodes for a series of queries. For instance, we might want to check if completing one course allows access to another. To solve this, the first step is to represent the graph using an adjacency list. This is because adjacency lists are space efficient, especially for sparse graphs, and they allow us to traverse the graph efficiently. We construct the adjacency list by iterating through the list of edges, where for each edge, A, B, we add B to the adjacency list of A. This creates a clear mapping of each node to its direct neighbors. The next step is to pre-process the graph by determining all reachable nodes for each node, which is essentially computing the transitive closure. This allows us to answer queries quickly without performing a full traversal every time. For this pre-processing, we can use algorithms like Floyd-Warshall or graph traversal techniques like BFS or DFS to calculate reachability for all nodes in the graph. Once we have the adjacency list, we use graph traversal to compute reachability for every node. For each node, we perform a DFS or BFS to find all nodes it can reach, and store the results in a dictionary called reachable. In this dictionary, each key corresponds to a node, and its value is the set of all nodes reachable from that node. The process involves iterating through all nodes in the graph. For each node, we initialize a stack for DFS and a set to keep track of visited nodes. As we traverse, we add each visited node to the reachable set of the current node and continue exploring its neighbors. This ensures we capture all possible paths from the source node. By the end of this pre-processing step, the reachable dictionary contains a complete mapping of reachability for every node, which will allow us to answer any query in constant time. With the reachable dictionary ready, we can now answer queries efficiently. For each query, U, V, all we need to do is check if V exists in the reachable set of U. This check is performed in constant time because it's a simple dictionary lookup. The results for each query are stored in a list, where each entry corresponds to whether the destination node is reachable from the source node. This approach highlights the key insights of the algorithm. First, pre-processing the graph to compute reachability eliminates the need for redundant traversals for each query, significantly improving efficiency. Second, there's a trade-off between space and time. While the reachable sets require additional memory, they allow us to answer queries almost instantly. Finally, the algorithm is robust enough to handle disconnected graphs, as nodes without outgoing edges will naturally have empty reachable sets, ensuring correctness. Let's analyze the complexity of this approach. The pre-processing step, where we compute the reachability for all nodes, has a time complexity of O(V*) plus E. This is because each DFS or BFS runs in O(V) plus E, and we perform it for all V nodes. Once the pre-processing is done, each query only requires O(1) time due to the dictionary lookup. In terms of space, the adjacency list takes O(V) plus E, while the reachable dictionary requires up to O(V²) in the worst case, where every node is connected to every other node. Now, consider some edge cases. For an empty graph with no nodes or edges, all queries will naturally return false. For disconnected graphs, unreachable nodes will have empty reachable sets. Self-loops are handled correctly, as a node with a self-loop is included in its own reachable set. Cycles in the graph are also managed seamlessly during traversal, as all reachable nodes are identified regardless of cycles. This balance between pre-processing time and query efficiency makes the algorithm highly effective for scenarios with a large number of queries relative to the graph size. This implementation solves the problem by checking reachability between nodes in a directed graph. First, we initialize a graph as an adjacency list and a reachability matrix to store whether one course can lead to another. The graph is built from the given prerequisites, where each directed edge represents a prerequisite relationship. To determine reachability between nodes, we use a breadth-first search, BFS. Starting from every course, we traverse its reachable neighbors and mark them as reachable in the matrix. BFS ensures all nodes that can be reached from a given start node are processed efficiently and avoids redundant processing by keeping track of visited nodes. Finally, for each query, we simply check the pre-computed reachability matrix to determine whether the first course in the query can lead to the second course. This avoids recalculating reachability for every query and ensures optimal performance. The overall runtime of the solution is O(n)³ in the worst case, where n is the number of courses. This comes from processing every node and its neighbors during BFS and the matrix lookups for queries. The space complexity is O(n)² for storing the reachability matrix and adjacency list. This approach is well suited for the constraints of the problem. Here, we start by defining the Java implementation for solving course schedule 4. First, we initialize the adjacency list and the reachability matrix. The adjacency list, represented as a list of lists, will help us store the directed graph where each course points to its prerequisites. The reachability matrix is a 2D Boolean array that will eventually store whether there is a path from one course to another. Next, we populate the adjacency list using the given prerequisites. For each pair in the prerequisites array, we add the second course as a neighbor of the first course in the graph. Once the graph is constructed, we compute the reachability for all courses using breadth-first search, or BFS. This ensures that we systematically explore all reachable nodes for every course. Lastly, we process the queries by simply checking the pre-computed reachability matrix. If the matrix indicates that the first course in a query can reach the second course, we add true to the result list, otherwise, we add false. The result list is then returned, containing the answers to all the queries. Now, let's take a closer look at the BFS method used earlier. The BFS function takes the starting course, the graph, and the reachability matrix as inputs. It uses a queue to explore all courses reachable from the starting course. Initially, the starting course is added to the queue. Within the while loop, we repeatedly dequeue the current course and examine its neighbors from the adjacency list. For each neighbor, if it hasn't already been marked as reachable from the starting course, we update the reachability matrix to true and add the neighbor to the queue for further exploration. This ensures that all accessible courses are visited and marked accordingly. By the end of the BFS traversal, the reachability matrix for the starting course is fully updated, allowing us to efficiently answer queries without recalculating the paths repeatedly. The problem course schedule 4 requires us to determine whether one course is a prerequisite for another. We're provided with the total number of courses, listed from 0 to number courses 1, along with a list of prerequisites. Each prerequisite is represented as a pair, A, B, indicating that course A must be completed before course B. Additionally, we have a set of queries where each pair, U, V, asks whether course U is a prerequisite for course V. Our objective is to return a list of Boolean values, where each value corresponds to whether the given prerequisite relationship exists for each query. For example, in the given input, there are 4 courses, and the prerequisites form a chain, 0, 1, 2, 3. We need to check the reachability for the query pairs, such as whether course 0 is a prerequisite for course 3. Solving this will involve efficiently representing the course dependencies and determining whether there is a path between the queried courses. To solve the problem, we begin by constructing a graph representation of the course dependencies using an adjacency list. This graph will help us visualize which courses lead to others. Simultaneously, we initialize a reachability matrix, which is a 2D array that tracks whether each course can reach another course. Initially, the graph is empty, and all values in the reachability matrix are set to false. As we process each prerequisite pair, we update the graph to reflect these dependencies. For instance, after processing the first pair, 0, 1, the graph indicates that course 0 leads to course 1. Similarly, after processing all prerequisites, the graph shows the complete dependency chain, course 0 leads to 1, course 1 leads to 2, and course 2 leads to 3. Next, we compute the reachability for each course using a breadth-first search, BFS. Starting with course 0, the BFS explores all reachable courses, updating the reachability matrix to reflect these paths. For example, from course 0, we can reach courses 1, 2, and 3, so the corresponding row in the matrix is updated accordingly. We repeat the BFS process for each course to fully populate the reachability matrix. For course 1, we determine that it can reach courses 2 and 3. For course 2, it can only reach course 3. Finally, course 3 has no outbound dependencies, so it cannot reach any other course. Once all BFS computations are complete, the final reachability matrix describes the paths between all course pairs. Using this matrix, we can directly answer the queries by simply checking the corresponding values. For instance, the query 0, 3 is true because the matrix indicates that course 0 can reach course 3. Similarly, 1, 3 is also true, while 3, 0 is false because there is no path from course 3 to course 0. This approach ensures that we can efficiently answer each query after determining the reachability relationships. Now, let's consider an edge case where there are no prerequisites between the courses. For example, if there are 2 courses and no dependencies, the graph remains empty, and the reachability matrix remains as all false values. Without any prerequisites, there are no connections between the courses, so we skip the BFS computation since no updates to the reachability matrix are necessary. In this case, when we answer the queries, such as 0, 1, or 1, 0, we find that both are false because there are no paths between any courses. This demonstrates that the solution handles scenarios where courses are completely independent from each other. Continuing with the edge case, the second query, 1, 0, also results in false because, again, there is no path connecting course 1 to course 0. The output for this example is simple: both queries return false, as no prerequisites exist. This scenario highlights how the algorithm gracefully handles minimal input cases and ensures there are no unnecessary computations when the reachability matrix remains unchanged. Finally, let's look at a more complex example with overlapping dependencies. Here, we have 3 courses, and the prerequisites include both a direct dependency from course 0 to course 2 and an indirect path through course 1. Representing these prerequisites in the graph shows that course 0 leads to both courses 1 and 2, while course 1 leads to course 2. Using BFS, we populate the reachability matrix to reflect all paths between the courses. For instance, course 0 can reach both courses 1 and 2, and course 1 can reach course 2. The final reachability matrix allows us to directly answer the queries. For 0, 2, the result is true because there is a direct path. However, for 2, 1, the result is false because no path exists from course 2 to course 1. This example demonstrates how the solution efficiently handles more complex dependency structures and ensures accurate results for all queries. When working with Course Schedule 4, there are a few common mistakes to be aware of. First, it's easy to overlook edge cases, such as disconnected graphs or nodes with no dependencies. For example, a node without any incoming or outgoing edges might cause traversal algorithms to fail if not handled properly. To address this, always test with scenarios like isolated nodes, cyclic dependencies, or even an empty graph. Another frequent issue is inefficient traversals, such as recomputing the same traversal for multiple queries. Running a full DFS for every query can be unnecessarily time-consuming. Instead, pre-process the graph to store transitive relationships using approaches like Floyd-Warshall or topological sorting. Lastly, choosing the wrong data structure can impact both memory and performance. For sparse graphs, an adjacency list is more efficient, while for dense graphs, an adjacency matrix may be more appropriate. Tailor your data structure to the graph's characteristics and your specific operations. Another critical mistake to avoid is failing to detect cycles. Assuming a graph is acyclic without verifying can lead to infinite loops during DFS or incorrect results in topological sorting. To prevent this, use a visited set or a parent pointer to identify cycles during traversal. Additionally, hard-coding constraints is risky. For instance, designing a solution that works only for small graphs might lead to timeouts when the input scales. Always analyze the problem's constraints and ensure your approach is efficient for larger inputs. By focusing on scalability and time complexity, you can avoid solutions that break under higher loads. Now, let's discuss some important insights for interviews. Recognizing common patterns in graph problems is crucial. Many of these problems revolve around traversal techniques like DFS or BFS, shortest path algorithms like Dijkstra or Bellman-Ford, or transitive closure methods like Floyd-Warshall or union find. Asking clarifying questions can also make a big difference. Questions like, can the graph have cycles, or is it directed or undirected? Understanding these properties determines which approach will work best. For example, pre-processing the graph to compute all pairs paths can significantly reduce complexity in scenarios with multiple queries. If standard methods like DFS or BFS seem too slow, consider alternatives like union find for connectivity or dynamic programming for transitive closure. Finally, during interviews, it's helpful to explain trade-offs between approaches. For instance, Floyd-Warshall is straightforward but computationally expensive at O(n cubed), while DFS for each query avoids pre-processing but can still be inefficient overall. Highlighting these trade-offs shows a deep understanding of the problem. It's also helpful to explore related problems to build a strong foundation. For example, LeetCode 207, course schedule, focuses on cycle detection in a directed graph using DFS or topological sort. LeetCode 210, course schedule 2, extends this by requiring the topological ordering of a DAG. LeetCode 547, number of provinces, involves finding connected components using DFS, BFS, or union find. And, of course, LeetCode 1462, course schedule 4, tackles prerequisite relationships across multiple queries. When considering alternative approaches, the Floyd-Warshall algorithm is great for computing all pairs transitive closure in a pre-processing step, but its O(n cubed) complexity makes it unsuitable for large graphs. On the other hand, running DFS or BFS for each query avoids pre-processing, but it becomes inefficient with high numbers of queries. Understanding these trade-offs will help you choose the best solution for each scenario. Finally, let's look at two additional techniques. Union find, or disjoint set union, is excellent for connectivity problems. It offers nearly constant time complexity for operations when using path compression, making it highly efficient. However, it's limited to undirected graphs and cannot handle directed edges or edge weights. Another powerful tool is topological sort, which is ideal for verifying dependencies in a directed acyclic graph. It's a great way to ensure tasks are completed in the correct order, but it's not applicable to graphs with cycles. Each of these methods has its strengths and limitations, so understanding when to use them is key to solving graph problems effectively. Great job! We've now covered the key aspects of Course Schedule 4, including the intuition behind the brute force approach and its potential limitations. Remember, mastering graph traversal techniques is crucial for problems like this. Thank you for watching, and I hope to see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!